We do have homework due tonight, so check it out. I hope you've had a chance to get it started. It's actually not, it's quite a bit shorter than last time, although the individual problems are, I would say, harder because they're these instantaneous rate of change things. We're going to do a couple more of those today and then move on to something a little bit different but pretty similar. So let's just get down to it. I wanted to do, maybe I'll refresh your memory about the formula for the instantaneous rate of change. F prime of A is, this formula you should eventually memorize. Limit h goes to 0, f of A plus h minus f of A divided by h. This is the instantaneous rate of change. Change. All right, the instantaneous rate of change. And it is a bit of a pain to work with this formula because you got to do a lot of algebra in order to compute that limit. A lot of expanding, sometimes, doing the FOIL thing and then canceling. I thought we should do at least one sort of real world problem about instantaneous rate of change. It is actually important in the real world, and I've mentioned this sort of offhand, but I wanted to write down some very specific examples. So this is, I will say, very useful in many types of applications. For example, if I have one function, now we're talking about rate of change. Usually this refers to something which is changing over time. Well, this doesn't always have to be, but you should generally think of this as something which is changing from moment to moment over time. And for example, if I have a function, this is sort of a physics type example. They usually write this function like this, s of t. So the variable is t because it represents time, and s represents distance. I think in physics they don't like to use d for distance because d means other things sometimes. But anyway, if s of t is my position or distance, I'll say position at time t, then what is represented by s prime of t? This would represent the rate of change of my position at a particular time, how fast my position is changing. Like if I'm in a car, my car is at different locations at different times. What does it mean to talk about how fast the location is changing? That's just like how fast the car is moving. And in physics, this is called the velocity. And of course, there are many, many situations when you care about the velocity, like all the time. This is super important in physics, but also just like in ordinary existence, right? So this is the classical example when the instantaneous rate of change is worth something. And actually, I think even the first homework assignment for today says something like, tell me the instantaneous velocity. I hope that wasn't confusing to anybody, but this is why the instantaneous rate of change represents the velocity. All right, how about, I'm just going to throw out some other random examples. How about this? If I have a population, P of t is the population, let's say, of people. Populations change over time, or you could, if you're into sort of medical type stuff, you wonder about, say, a population of growing bacteria, or a population of, they use the word population for like cancer cells which are spreading. In that case, the population would be bad. Anyway, if P of t is the population of something or other at time t, then what is this P prime of t? This would mean how fast is the population changing at a particular time. So this is the rate of how fast it's changing. And just like in the, when we talk about the average rate of change, we had some examples. that can be either positive or negative. Positive means a change where the thing is getting bigger. And negative means a change where the thing is getting smaller. So in this case, this is the rate of how fast the population is changing. Maybe I shouldn't have said it's. What I meant is the population. And in particular, if it's positive, if P prime is positive, I just said it's again. That means that the population is increasing because it's just like the average rate of change. When the rate of change is positive, that refers to an increase at a particular rate, and if the rate of change is negative, that refers to a decrease. So if P of T is negative, the population is decreasing, right? And these will be interesting for various reasons depending on what you're talking about. If you're looking at like a population of cancer cells, you do not want the population to be increasing very fast, and it'd be great if it was decreasing, right? And this is the instantaneous rate of change is the appropriate way to measure that. These are both examples, this velocity and then this population thing. Those are both examples where you're talking about a rate of change over time, although it doesn't have to be over time. You can have one thing which is changing based on another thing, and the other thing doesn't have to be time. So here's another example. If this is more of a sort of business type example. If C of X is the cost to make X things, like if I'm, making, I don't know, shoes or something. Of course, if I make 0 shoes, that doesn't cost me anything. If I make, 100 shoes, that will cost me a certain amount. If I make 200 shoes, that costs a certain amount. So this is what my function is. C of X is the cost to make X things. Now, this has nothing to do with time. I'm just saying for different amounts of whatever I can make, it will cost me different amounts to actually produce them. And then what is the rate of change of that represent? Then C prime of something. This means how is the cost changing if you change the X? So this is no longer a change over time because I'm not talking about time at all. I'm just talking about the cost of making a certain amount of things. This is the rate of change of the cost when we change the X, all right? That is to say, if I decide to make a different amount of shoes, how fast will the cost, what it will be, not how fast really, but what will be the effect on the cost? Will the cost increase if I decide to make more shoes, or will it decrease if I decide to make more shoes? That kind of a thing. All right. So it doesn't. This is a weird example, but it doesn't have to do with time. It doesn't always have to do with time. That's what I wanted to try. All right. There's a name for this. This is referred to as the marginal cost. I don't know if you heard of this kind of thing. If you're taking a business class, the marginal cost. It means this does not represent the total cost of making all the shoes. It just means how much extra would it cost me if I were to make a little bit more. That's the marginal cost. How much would the total cost change? It's the rate of change of my total cost. If I decided to make a little bit more, how much more is that going to cost me? That's called the marginal cost. So these things are super important. And you can talk about marginal cost, but you can also talk about other things in business, the marginal profit, marginal revenue, that sort of stuff. These are all related to instantaneous rate of change of something or other. All right. I got one sort of made up real world example. I wanted to just do, this is kind of like a word problem, right? Involving the instantaneous rate of change. That's a little more interesting than just velocity or something. So this is inspired by true events. Let's say I'm making maple syrup. This is a true story. I do make maple syrup. I have a big maple tree in my backyard. I live nearby, and I tap that thing. let's say that's a true story. This is a made-up formula I'm going to give you here. Let's say it costs this much. I'm going to give you a formula to make X jars. I put them in little glass like jelly jars, just because maple syrup it takes a long time to make even a little bit, and so I don't make very much from this one tree. Let's say that it costs this much to make X jars. My expenses really is just the power. All you do is take the stuff out of the tree and then boil it for a long time, and I do it on my gas grill. Grilled maple syrup. That's my expense. The cost is the gas. All right, let's say that it costs me this much to make X jars. So if you want to know how much does it cost to make one jar, you plug one into that formula, and that will tell you. How much to make 2 jars, you plug 2 in, and that will tell you. All right, this is a made-up formula. This is not terribly realistic. Okay, what I would like to, I'm going to actually figure out the instantaneous rate of change. But before we get to that, let's just talk about what does it mean. So this is often asked in the book questions, and I'm probably going to ask you something like this on one of our test questions. What is the interpretation of C of 5 versus C prime of 5? What do those things mean, each of them? We can just say a few words. I'm not asking you to write me a big novel here. What does C of 5 represent? This is the easier one to describe. I said it costs this much to make X jars. So what does it mean when I say C of 5? That, of course, means you plug 5 into this formula. You get some number as the answer. Anyone think you can say, what does that number represent? If I were to plug in 5 here. You can tell from all the words I said. Yeah?
If you make 5 jars of maple syrup.
Yes. Then what does this represent?
Oh.
I'm expecting you to say the C word.
Oh, the cost.
The cost, yeah. I think that's what you meant.
Yeah.
This is the cost if you make 5 jars of maple syrup. That's what C of 5 represents. So C of 5 is the cost to make 5 jars. All right, and if you like, you can say exactly what that is. I mean, this is not hard. You plug 5 into that formula up there. It would be 0.001 times 5 squared plus 1.5 times 5 plus 20, which is something or other. I plugged this into my calculator. I got 27.475. That's half a cent on the end there. But anyway, that number there represents the cost to make 5 jars of the maple syrup. That's C of 5. All right? Any questions about that? That has nothing to do with rate of anything. That's just because I told you the formula represents the cost. Okay, what about C prime of 5? This is much harder to figure out what it is, but can we say in words, first of all, C prime of 5 is the marginal cost when I make 5 jars. What that means is, how much would it cost to make just one more at this point? So when I'm making 5, it cost me $27.475. But how much more would it be if I made a little bit more? So the meaning of this, the marginal cost, is this is how much more it would cost if I decided to make one more jar. When I was already making 5, if I said, you know what, I'm going to do 6 instead, how much more would that be? That's what this quantity represents. It's how much the price would change if I decided to increase my production by 1. this is what it means to say the rate of change when I change the amount that I'm producing. How much the total cost would change. How much more cost would there be? All right, it's a slightly complicated concept, I suppose, but it's not so crazy. Okay, now let's actually sort of do the math here. What really is this as a number, right? It should be some number. I would expect, just based on what I said here, I would expect this number to be actually a lot less than 27, right? 27 is how much it cost me to make all 5. And now I'm asking, how much more would it be if I instead made 6? It's probably, I don't know, 2 or 3, like quite a bit less than this is all I'm saying. Let's see what really happens here. So let's find C prime of 5. Now this is the most sort of mathiest part of this question, but when I give you questions like this on the test, I'm probably going to ask you some kind of interpretation type thing here, like this, which you just write a simple little explanation, and then I'll also ask you to figure out what this is. So you need this formula here. I'm just going to copy it down there so I don't have to scroll. And here we're going to do a fairly complicated instantaneous rate of change formula. So it's going to be C prime of, oh, my pencil's losing it now. C prime of 5 is, all right, you do this lim thing, right? It's f of a plus h minus f of a. Now, instead of f, the function here is called c. So would you mind if I said c of a plus h minus c of a divided by h, where a is 5 in this case. So it's really c of 5 plus h minus c of 5 over h, like so. All right, this is just, remembering the formula. Now, our first hard step is doing the actual plugging in, c of 5 plus h, all right? Remember, we did several examples of these last time, and I hope you've tried them out on the homework on your own. What this means is I go up to this formula here. This is the formula for c, and instead of x, I'm putting 5 plus h. So I'm going to write all this stuff again, but everywhere I see x, I put instead 5 plus h. So this says, I still have lim on the front, of course, minus 0.001 times 5 plus h squared plus 1.5 times 5 plus h plus 20. All right, all of that is this formula here, but instead of x, I put 5 plus h each time. So instead of x squared, I have 5 plus h squared. Instead of x right here, I have 5 plus h. All right, that is just this part of the numerator. So continuing the numerator, I now see minus, and then c of 5. C of 5 means you go up here and plug in 5 for x everywhere. So this looks like, don't forget the parentheses here, haters. Sorry, no x here. It's 0.001 times 5 squared plus 1.5 times 5 plus 20, like so. And then all of this is over h. All right. That step, I don't know if it looks easy when I do it, but this is one that's easy to get confused with. All we're doing is we're going up here and replacing the x, first of all, by 5 plus h. That's this part. And then minus, again, replacing the x by 5. That's this part. All right, let's continue. So from now on, it's just a bunch of sort of simplifying, expanding kind of stuff. One thing you can do is do all these numbers inside the parentheses, right? And in fact, that's the same number that we did up here, isn't it? It's that. It's 27.475. So this stuff in the parentheses is 27.475. The rest of it, we have to do a little bit more work with. So on the front here, I'm going to do the FOIL with 5 plus h. This is a coefficient which I'm going to have to leave like it is for now. Minus 0.00. Come on now. All right, I'm doing 5 plus h, 5 plus h, right? Next, I have 1.5 times 5 plus h in parentheses. We can distribute here. Unfortunately, the numbers are a little weird here. Oftentimes on these applied problems, you might want to use your calculator to do little multiplications. On a test, of course, I will do this. I'll give you numbers that are nice. Anyway, I'm going to distribute 1.5 times 5, that's 7.5, and then plus a 1.5 times h. And then plus 20, which was there before. And then minus, and remember I said all that stuff inside the parentheses is the same number we calculated before to be 27.475. All right. These decimal numbers are kind of a pain to deal with, but not really so bad. You just got to keep it straight. Okay, let's continue then. I think the next thing to do is do the FOIL right here. All right, everything else looks pretty good to me, but I'm going to do the FOIL right there. This coefficient, again, has to just stay like it is. I'm eventually going to multiply it, but not yet. Come on, man. My pencil gets messed up. Same point. All right, do the FOIL. 5 times 5 is 25. In the middle, I got h times 5, and on the outside, I got also h times 5, so that adds up to be 10h. And then on the end, I got h times h, which is h squared. Continuing, plus 7.5 plus 1.5h plus 20 minus 27.475. And then the last sort of expanding step is distribute the negative 0.001 there. So it's minus 0.001 times 25. That makes minus 0.25 plus 0.001 just means like I shift the decimal point 2 positions to the left, or 3 positions to the left. So 10h becomes 0.01h. Sorry, these should be minuses, not pluses, because I am distributing this thing, which is a negative number. So that's a minus 0.001 h squared. All right, and then everything else like it is. This one's kind of a pain because of the weird numbers in there, but they're only numbers. They can't hurt you, all right? I wanted to do at least one example with weird numbers in it. Most of the examples we do will not be messy like this. Anyway, now we are going to try to combine the various parts of this. Combine the constants. What do we have for constants? Minus 0.25 plus 7.5 plus 20 minus 27. So 7.5 plus 20 is 27.5. And then I subtract that. Actually, it makes this, don't it? I think 27.5. Sorry, this first, I messed up the decimal point. It should be 0.025. Come on, man. That first number on the front there, I wrote 0.25. It should be 0.025, which makes this properly add up. So these constants will cancel, which is what I always hoped for. This, and this, right? 20 and 7.5 and negative 0.025 adds up to 27.475. All right? I like that. And then what's left over? I have negative 0.01h and then also a 1.5h. So to combine these two, it's 1.5 minus 0.01. It's 1.49h. You can use a calculator to do that if you like. Like this. We're almost done here with slightly weird numbers. Any experts on this? What should we do next? Towards the end, these all kind of look the same. Yeah. Factor out h on the top. Great. So it says h 1.49 minus 0.001h divided by h. Then cancel the h's finally. Oops. And we are left with just 1.49 minus 0.001 h. And then we plug in h equals 0 to take the limit, and all that remains is 1.49. That's the answer. It was quite a journey. This is what I said, the homework assignment for tonight is not very long. Not very many questions, but each question is going to take you a while to do. I think there's 5 of them, so they're not all hard, weird numbers like this, but check them out. All right, this is the instantaneous rate of change. And can we just for our sanity, does this number make sense given the question that was asked? Remember, it was about this business about the jars of the maple syrup. So to make 5 of them cost this much. How much, remember the meaning of this question would be, how much more would it cost to make 1 more? And we ended up saying 1.7 something or other. So it means 1.49. It means if I was already making 5, but I wanted to instead consider making 6 instead, that 6th one would cost this much, which makes sense. At least it's not way off the numbers, all right? Anybody got questions about that? This was a hard one. I was, thinking of trying to squeeze this in at the end last time, but didn't quite make it. All right. Excellent. That's the end of talking about the instantaneous rate of change per se, but we are immediately going to talk about a very closely related thing. And this is some words that I've said many times before. The derivative. I've said those words as sort of a preview. This is really the major topic for this semester, and it's what most of the things on our checklist of topics mention, the derivative. The derivative is actually just kind of a fancier way of saying instantaneous rate of change. But what the derivative represents is, I'll say it this way, when we have some function, f of x, we can discuss the instantaneous rate of change at any point x, like f prime of x. So f of x represents some ordinary function. F prime of x means it is a function which represents the rate of change of the original function, all right? We can discuss the instantaneous rate of change for various different points, and you get another function. So the idea is you start with one function, which describes something in real life or just abstractly. Then you can talk about how that original function is changing from point to point, and that gives you this other function, f prime of x, and that's called the derivative. So this f prime of x as a function is called the derivative. All right. In the definition of the derivative, so what's the difference between the derivative and the instantaneous rate of change? It's not really much of a difference at all, but the main difference is the instantaneous rate of change is a specific number, but the derivative represents an entire function of rates of change. So the definition, here's the definition of the derivative, f prime of x. It's the same instantaneous rate of change formula. The only difference is I'm using x everywhere instead of a. And so in this formula, it's the same formula as the instantaneous rate of change, but the only difference is that x stays as a variable. You never plug some value in for a. All right? And x will remain in the answer. Because you're never going to plug in anything for x. The answer is another function, so it will have x's in it, not just a number like the instantaneous rate of change that we've been doing. You always just get a number at the end. This is a whole function describing various different rates of change. All right. Let's see if we can do an example like this. It's really the same procedure. It's just that, you know, what I said in the parentheses there. X stays as a variable. You don't ever plug in some value. So, for example, how about what is the derivative of x squared? X squared is one function. I would like to know what is the function which describes the derivative of x squared. So my f of x is x squared, and then I do this f prime of x thing with the same old formula. So it's f of x plus h minus f of x divided by h, right? That's the definition of the derivative. And then we're going to do this limit, like I said, without ever plugging in specific numbers. You just leave the x as an x the whole time. The h, we will eventually, as always, at the end of this is going to end with plugging in 0 for h. So we are going to do that eventually, but you never plug anything for x. X will just be part of the answer. All right. So anyway, we're going to do the same procedure. So we begin with that first step is the plugging in, which is often the hard step. F of x plus h. This is not such a difficult example. It means you go up to the function definition here, and I'm going to replace, instead of x, I use x plus h right here. So it says x squared. I replace x with x plus h, and it will now say x plus h squared. So that's the f of x plus h part. This part right here turned into that. It's because f of x is x squared, so when I replace x with x plus h, I get x plus h squared. All right, minus comes next, because there's a minus right there. And then f of x, that's just this. You just write that as is, divided by h. All right. This is how we start it. And then you do the same old kind of simplifying stuff. These are, I would say, maybe a little bit harder just because there aren't a lot of numbers in there. In the examples we've been doing so far, there's some numbers and some h's. Here, instead, you have some x's and some h's. No problem. It's the same procedure. It's just it looks a little different. What should we do here? Anybody have a suggestion? It's similar to the usual simplifying stuff that we do. What do you think? My red lines. What shall we do? Yeah? Yeah, do the FOIL thing right here. X plus h squared. Do the FOIL on that. Thank you. We're hiring a new professor in the math department this year. This guy just came yesterday to do like a bunch of interviews. And we had him go to somebody's class and do like a guest appearance. And he was asking a lot of questions, and those kids in that class did not want to answer anything he said. I felt bad for him. They were killing him. Whenever someone said something, he said, "Wonderful." That was his catchphrase. Thank you. Okay, you do the FOIL here. X plus h times x plus h. So the ones on the front, I get x times x, which is x squared. In the middle, h times x. And on the outside, x times h. Those are actually the same, and they add together. You get 2x times h. So this is plus 2x times h. All right? That's a xh in the middle and a xh on the outside. They add up to 2xh. And then on the ends, I have h times h, which is h squared. All right? That's the FOIL there. That was just the FOIL part. Then I continue. Minus, next comes here, minus x squared. So there, minus x squared divided by h. All right? I hope I'm doing okay so far. Next, you do the, hopefully we can cancel some stuff here. Now in the other examples, you always are trying to cancel all the constants, and if the constants don't all go away, then you messed it up. In this case, there aren't typically going to be a lot of constants, although you should still be able to cancel everything here which has no h's on it. And in this example, I see x squared and a minus x squared, and they will cancel. So I cancel this guy and that guy. And what remains, you will notice everything that's left has h on it. And that is what you're looking for in this type of example. If that doesn't happen, it means you messed it up. Anyway, 2xh plus h squared divided by h. And we finish, as usual, by factoring the h on the top and then canceling. So I go factor out h on the top. What remains is 2x plus h. Cancel the h's. Ugh, come on. (2x plus h). And then finally, we finish by actually doing the limit, which means I plug in h equals 0. What do I plug in for x? The answer is you don't plug something in for x. X will be just part of your answer. So I get 2x plus 0, which is 2x, and this is the answer. All right, that is the derivative of f of x equals x squared. All right, so just to summarize that, for f of x equals x squared, we got f prime of x equals 2x. All right, it is a true fact. The derivative of x squared is 2x. You can ask any calculus student this question and they should know. The derivative of x squared equals 2x. And let me just say what this represents. This means the instantaneous rate of change of x squared at some point x is always 2x. All right, and this, of course, instantaneous rate of change is also the same as the slope of the tangent line. This is what we talked about before. All right, the instantaneous rate of change is the same, geometrically speaking, as the slope of the tangent line. All right, those are the same thing. The instantaneous rate of change of x squared at some point x is always equal to 2x. This is a weird thing, but it's true. Maybe I could just try and draw a picture. This isn't going to be super accurate, but x squared, of course, is the parabola like this. Yeah, it looks pretty good. And what I'm saying is the instantaneous rate of change at any point is always equal to 2x. Like if I look at, say, 1 here, and I ask you what's the instantaneous rate of change, it's the slope of this line. And would you believe me if I said at x equals 1, this slope is 2. 2 times 1, which is 2. This 2x here gives you a formula for the slopes, depending on what x is. So at x equals 1, this slope is 2. Would you believe that? That means that it goes over 1 and up 2, which looks pretty accurate on this picture, right? Whereas if I went to x equals 2, say, that would be up here, say this point. The slope here is quite a bit steeper, the slope of the tangent line, maybe more like that. And would you believe me, the slope right there is equal, sorry, my picture's a little crowded here. The slope here is 2 times x, which will be 2 times 2, which is 4 in this case. All right, this is the kind of geometric meaning of this derivative formula. It tells you all the slopes, or in a real world problem, it tells you all the instantaneous rates of change of whatever you're trying to talk about. All right. I got one more that I'm going to do, and then I got some for you all to try, right? Let's try one more here. So x squared was that example. This one is going to be a little bit fancier. How about f of x equals 2x squared minus x plus 1? This is about as fancy as they're going to get. So if you can follow this one here, then you should feel good about this kind of problem in general, although I'm going to ask you to do some. So your job, find f prime of x. That's the derivative of the first function. This would represent the slopes along the graph at each various point, or it would represent, in a real-world problem, the rate of change of something or other. All right. Don't think too hard to begin with. You use the formula. So again, this formula you will need to have memorized before too long. Our first exam is a week from Friday, so by then you should know this formula. All right, that's the derivative, the definition of the derivative, and then we just start plugging stuff in here. F of x plus h. Immediately, this is like the hardest part of the plugging in step. F of x plus h. It means I write this formula out again, but instead of x, I use x plus h everywhere you see x here. So it begins with 2 times x plus h squared. That's this part. I just did the 2x squared part, but instead of x, I use x plus h. Then minus, then x. Instead of x, I use x plus h, then plus 1, right? Make sure you put the parentheses around the x plus h there, because you're going to have to distribute the minus sign. It all matters, unfortunately. Okay, that much was just this part, f of x plus h. Next I see minus, and then f of x. That means just this as is. You just copy this into this position. You should put parentheses around it because the minus sign will have to distribute. 2x squared minus x plus 1 over h. All right, that's the plugging in step. It's a little complicated. It can be a little confusing. All right, from here, we're going to do a bunch of FOIL type simplifying. So I have that 2 there at the beginning. It's going to have to stay like it is. X plus h squared, I'm going to write as x plus h times x plus h, and then I'll expand that out in the next step. What else can we do here? Next, I see minus x plus h. Distribute the minus sign here. That becomes minus x minus h. You've got to distribute. Then, next thing I see is plus 1. Okay, I can do plus 1. And then minus. Here I'm going to distribute the minus sign across this whole thing. And it'll be minus 2x squared plus x minus 1. And I hope I didn't mess it up. Divided by h. There are many chances to mess it up, unfortunately. Okay, next I'll do the FOIL on the beginning. Lim h goes to 0. The 2 here, and then x plus h times x plus h. On the front, I get x times x, which is x squared. In the middle, I get hx. On the outside, I get xh. That adds up to 2xh. And then on the end, I got h times x, which h times h, which is h squared. All right? And then the rest of it. Minus x minus h plus 1 minus 2x squared plus x minus 1 over h. And then finally, I'm going to distribute the 2, and then I'll be ready to start canceling stuff out. Distribute the 2. 2x squared plus 4xh plus 2h squared minus x minus h plus 1 minus 2x squared plus x minus 1 divided by h. All right. Now we can start canceling stuff out. Anybody see anything that will cancel up top? There should be some things that just directly cancel with other things that you see on the top. What do you think? Yeah?
2x squared.
2x squared. Yeah, I have a 2x squared and a minus 2x squared, so those will cancel. What else? I see more. Yeah?
No, plus 1 and the minus 1.
There's a plus 1 and a minus 1. Yeah. And I see one more thing that cancels entirely. Yes?
Plus x and minus
Plus x and minus x. Wonderful. minus x and plus x. Yeah, great. Okay, so what remains is 4xh minus h plus 2h squared divided by h. All right. And again, remember what you're looking. All right. What you're looking for in this step is that everything that remains should have a h in it, which it does in this case. If you get a piece that remains there that doesn't cancel but it has no h in it, then it means you messed it up somehow. All right. So since everything up top has a h on it, I can factor out the h. This is just the same way that these always finish off. Factor h on top. What remains is 4x minus 1 plus 2h. This h here became a 1 when I factored it out, because factoring is like dividing and multiplying. So this is like h divided by h is 1. All right, then I cancel the h's. We're almost done here. Cancel the h's. I am left with lim h goes to 0. 4x minus 1 plus 2h. And we finish by plugging in h equals 0. The 1, the 1, and the x will stay like it is. So this becomes 4x minus 1 plus 2 times 0. And my final answer is 4x minus 1. There you go. That's what it takes. Any thoughts about that one? This is how we do it. All right, I got one. I got two for you to try. The first one is easier, and I'll just for fun, I'll tell you the answers. Find the derivative of first one, f of x equals 4x. And the second one, f of x equals x squared minus 4x. All right. And now I said I would tell the answer. The answer for the second one is 2x minus 4. And the answer for the first one is 4. This is a little weird, but actually in the first one, all the x's cancel by some coincidence, and you just end up with a number. Usually your answer will have x's in it, but sometimes, of course, it can be that the x's go away. All right, check them out. See what you think. I will come around and see how you're doing. it's 4, and then this x. Yes, this x. Yeah. It's very close to it. Okay. Can I make a suggestion?
Yeah.
This is not quite right. You do this step. This step means you write this formula, but you replace x and you replace x.
Oh,
So
okay.
just put a h on the end, which is.
Yeah, okay.
All right. Got 4 here?
Yes.
Great. How's it going? Doing okay?
Because I don't think I would get.
Yeah, no, this is good. Here you need to distribute 4.
Oh, it's 4.
Yes.
Oh, okay.
Now I feel better.
Yeah, thank you.
All right. Okay. 4. Yeah, so this one is this f which means here's at the x. So you write this again, but instead of x, you say x is all by itself.
Yeah, like minus 4. And then put it minus 5. And then minus x squared minus 4x.
How's it going? You get 4? Yes. Then you want to cancel each here. There's not each.
So I just cancel those out. So I didn't have to do
You just get 3. Yeah, you get an extra each. This would actually be 4 times it. Okay. Yes, I think that,
Yeah.
oh, that's good. I just wrote that 4. It wouldn't matter eventually.
Yeah.
Doing okay? Yeah, great. How's it going? You got something? Yeah. Doing okay? This is, it says 4x, but on this step, you should be replacing x. It's really just 4 times x. Yeah, so it's.
So if there's 4x squared, 4x,
Just 4x.
or 4x h minus x.
Like I do.
Just the word h.
No.
And then this part should have been the choice.
Oh my god, that's so tough.
This is a section. Yeah, that is not. How's it going? Yes? Yeah. All right.
Yeah. I'm just curious. Like, if there's any minus x, you just I don't know how to go against them. Is this like, so do I
That's
do
true, yeah.
minus x minus h? It's just minus 4, and then these are minus x squared minus, right?
This would not. Four. Minus 4x. But plus. But this is actually. So this part, that's good to start, but then you go minus 4x.
Okay, so this would be. Minus 4.
much.
Yeah.
This is
I'm going to
okay. And a little minus.
I think it's in nursing, so I'm going to just minus. Is it just square roots? Okay. I think it's like.
All right. Yes, that's right. Yeah. Yeah. Yeah, so you start with this f of x plus h.
Mhm.
And then you go to all this stuff. Instead of x, you use
Yeah, so that's it works. This becomes. So, yeah, so it's x so x plus h.
no, like this is the f. So when you say f of x, plug in x plus h, that's all x here.
Oh.
So it's times x plus h.
Doing good?
Well,
I mean, technically, what you're writing here is not correct.
Negative y minus.
Yeah, you just choose not to write it.
No, okay, I was just wanting to.
I mean, I wouldn't take points out for it.
There's also.
That is correct.
Oh, it's tomorrow.
Alright, that's your own life.
Oh my god, I thought it was tonight. I know, I had a gap tonight.
it looks pretty good. The last step.
No one wants to be my roommate. Yeah, that's good. I know. I asked her. She's like, yeah, I usually get to finalize by next week. I'm just like following. If it's back, it's like the 26th. No. She's gonna drop it. It's like fine.
I like that. This is the very first step. So sum of this simplified. Alright.
Two C's and
Okay.
two R's?
Yeah.
Oh yeah, that's what I thought. That's what I thought. A-R.
That's good. Yep. It wasn't
Also loyalist.
All right, I want to talk about these. I see some people finished them, some people not quite. That's all right. These are, like I said last time, I consider these to be quite difficult. Once you get the hang of it, it's not so it's not so bad, but it does take some getting used to. So for the first one is the easy one. F of x equals 4x. I go lim h goes to 0. F of x plus h. This is the formula, minus f of x over h. So this is f of x plus h means I look at this function and I plug in, instead of x, I plug in x plus h. So it will say 4 and then parentheses x plus h. It used to say just 4x, but I changed the x into x plus h. And then minus, right here, minus f of x, that's just 4x. Like so, divided by h. And now what do we do to simplify? This one, there's no FOIL involved. You just distribute the 4. It works out nicely. 4x plus 4h minus 4x divided by h. You cancel the 4x's. All that remains is 4h. So this is lim 4h divided by h. And now I can cancel the h's, as we usually do, and then all that remains in the end is 4. And that's just 4, all right? This is a little strange at the end here. It's the limit as h goes to 0 of 4. That is just 4, though, because what this lim means is it means you should plug in h equals 0. There is no 0, there is no h here, so nothing happens when you plug in 0. You just get 4 as the answer. Anyway, everybody got this one. Anyone have any questions? As I was going around, I saw people did this one just fine. All right, the other one is a little more interesting, maybe. You just have to get it started right and then don't mess it up. That's kind of, unfortunately, the only sensible advice that I have here, because it is easy to mess it up. So the very first step is sometimes the hardest one. You plug in x plus h. It means I'm going to write all this stuff, but instead of x every time, I write x plus h. So I get x plus h squared minus 4 times x plus h. That's what you get when you write this, but I use x plus h instead of x. It's x, instead of x squared, I get x plus h squared. Instead of 4 times x, I get 4 times x plus h. All right, that was just this part, f of x plus h. Now I go minus f of x, which is the original formula exactly as is, and then divide everything by h. And now we should just do a bunch of simplifying. So we need to do the FOIL on the first thing, x plus h, the whole thing squared. Would you mind, since I'm a FOIL master, I know this ends up looking like this. You might, I don't know if you like memorizing things, you might want to memorize that x plus h squared equals this, because this just comes up in many of these problems. Or you could think it through every time. Up to you. Next, I see minus 4x plus h. I distribute the 4. I get minus 4x, minus 4h. Then next, I see minus x squared plus 4x. I distribute the minus sign there. Minus x squared minus 4x, like so. Everybody with me so far? I hope so. Now it's just a matter of canceling things. I see x squared at the beginning, cancels a x minus x squared. I see 4x in the middle there, minus 4x, and another minus 4x. Oh, that's because I messed it up. I don't like that because I wanted them to cancel. Sorry, nobody noticed. This was a minus here. I wrote a plus here. I'm just being silly. It should have been a minus here, which means when I distribute the minus sign, this one should be a plus, which means it really does cancel. All right. Sorry about that. It happens to all of us. Okay, and I think that's all that cancels directly. So it's lim h goes to 0. 2xh plus h squared minus 4h divided by h. Then I factor h on top, as always. H times 2x plus h minus 4. That's what you get when you factor h out of that stuff. And then finally, we can cancel h's and take the limit by plugging h equals 0. So this is lim h goes to 0. 2x plus h minus 4. Plug in h equals 0, I get 2x plus 0 minus 4. 2x minus 4 is the answer. I got it eventually. Any questions about that? If you weren't able to do it, then it's probably because you just messed up something silly in the middle, or maybe, I mean, this first step is the real sort of substantive difficult step. The rest of it is just a matter of kind of high school algebra, which of course is not always easy to do, but at least it's, you don't have to, there's no big ideas involved. All right? Great. I would like to say a little bit of something about the next section. So this is the end of this section on our checklist. This is called the definition of the derivative. That's number 7 on the list. The definition of the derivative, and finding the derivative using this limit formula. The next thing on the list is called derivatives on graphs, and we got 10 minutes left. That's enough to do our first example, at least, and then we'll do a slightly more complicated one next time. Derivatives on graphs. Derivatives on graphs. Remember, if I give you f of x is a function, so for a function f of x, this other function, f prime of x, is another function, and what it represents is the instantaneous rate of change of the first one, or equivalently, it represents the slopes of the first one. And for now, I want to talk about derivatives on graphs. So I'm going to think of this in terms of slopes, because that's the most sort of graphical interpretation. So for a function f of x, f prime of x is a function representing the slopes. The slopes of f of x. I say slopes because the original function, it has a different slope at every point. assuming it's not a straight line. And so those various slopes is what this other function is just describing. All right, so for example, even if I don't give you an equation for something, just like I could show you a picture, and you can still say a lot about the derivative. I'm going to try to draw a function like this. Like that, all right? And I would like to say, what can we say about the derivatives of this function? For example, can we sort of eyeball estimate f prime of 2, let's say, and let's say 2 is like here, so it's that point on the graph, f prime of 2. I'm going to say it looks like, well, what does that mean in terms of the graph? It means the slope of the tangent line at this black point here, where x equals 2. So this is x equals 2. That means the slope of the tangent line here at this point. All right? And can you kind of estimate this? I mean, this is not an exact science, but remember the tangent line means a line which just touches that graph right at that one point. This is not a good tangent line. How about that? Yeah, something like that, right? I'm talking about the slope of that straight line. It's the tangent line right there. Any slope masters? What would you say the slope of that is? I'm talking about the rise over the run. Approximately. You want to think about, if you were to sort of turn this into a triangle. It goes over some and up some. What's the? It's like a 45-degree line. Anyone remember what the slope of such a line is? Nobody wants to say. Like in my triangle here, if this triangle goes over 1, just because it's a 45-degree line, it means it goes up by 1 also, right? That's kind of what a 45-degree line does. So,
Y over changing x.
yeah, it's the change in y over change in x. What would you get in this case if you did that? I mean, you can say like a specific number. It looks to me like this is going. It looks to me like this is going over 1 and up 1, right? So what would the slope be? You want to show me on the fingers? Sometimes nobody wants to say it out loud, so I ask for the fingers. Yes. The 1. Yeah, thank you. Wonderful. The slope of the tangent line here looks like plus 1, right? A 45-degree line is always slope plus 1 if it's going up to the right. If it's going down to the right, that's a slope minus 1. All right? So in this case, f prime of 2, it looks like about 1, right? Of course, I just drew this by hand, so it's probably not exactly 1, but something like something close to 1. All right. Here's another related question. Can we say for which x is f prime of x equals 0? Is there any place on this graph that you can see where the slope is 0? 0 slope means that the line is straight up horizontal, right? Does anybody looking at the graph here, can you see a place where the slope is 0? I'm going to maybe erase this triangle here just for now. Whoa. Anybody see any points where the slope is 0? That is, if you were to draw the tangent line, it would be a flat horizontal line. Are there any such points? Yeah?
-2 and 1.
She says -2 and 1. Yeah, I agree. Right here, this is -2. The point is there, And I hope you agree, the slope right there, if I were to draw the tangent line, is straight up, flat, horizontal. That is slope 0. And also, she said -2 and also 1. 1 is here, that's this point. And again, the slope is flat at that point. All right, so for which x is f prime of x equal to 0? The answer is for x equals -2 and x equals 1. All right, these are the points. So I'll just say here, the slope of the tangent line is horizontal. All right. Points where the slope equals 0 are actually very important in a lot of applications. So this is something specifically, that question is something we're going to be talking about a lot later on in the future. Maybe I'll just ask one more question. Can you tell me for which x's is the slope positive versus negative? For which x's is the slope positive versus negative? Maybe I want to scroll down, so I'm going to just grab this again. For which x's is the slope positive versus negative? Positive. And I want to give my answer in terms of intervals, because your answer is going to be something like, well, it's positive from here to here, and it's negative from here to here. So let's write the answer as intervals. Now, what does positive versus negative slope means? Remember, for a line, positive slope means it's going up and to the right. Negative slope means it's going down and to the right. I'll just write that down. Positive means up and right in terms of the direction that this line is going, and negative means down and right. All right. I can see, I don't know about you, I can see some intervals. For example, remember, she said a moment ago, these 2 points are where it equals 0. What about to the right of this point? For these x values, would you say the slope is positive or negative? Show me the thumbs. Positive, negative? I see some of the thumbs in the positive direction. Yeah, the slope here is positive throughout this region, because if you were to draw these tangent lines, they would all go up and to the right. They're not going down, right? That would be a negative slope. So in this region, the slope is positive. So for the interval, so if I were writing that like an interval, I would write it this way: 1 to infinity, the slope is positive. Right? That's this region right here. And I wrote 1 to infinity because I'm giving you the interval in terms of the x values. X equals 1 is right here, and then everything to the right of that. All right? I see an interval where the slopes are negative. Can anybody say? There is an interval where the slopes are negative. That is, the curve is going down in this region. For something else, the slope is negative. Anybody can say from here to here, the slope is negative. What do you think? -2 to 1. Yeah, thank you. It's time to go soon. You better speak up. Yeah, from -2 to 1, that's this region in the middle here. The slopes are negative because the curve is going down as you go to the right. And then back here, it's also positive. So that would be, if I were writing that as an interval, it would say, or -infinity to -2. That's to the left of -2, back here. Again, the slope is positive. The moral of the story is you can say a lot about the derivatives even if I don't show you the formula. Like, I never gave you the equation for this, but you can still just look at the graph and you can say a lot about it. All right, more on this next